Now I'd like to have a discussion on finding probabilities if there are two or more trials taking place with a given well-defined random procedure. Now when I say two trials, what I'm talking about is given two trials, we usually specify a particular event for the first trial and then another particular event for the second trial. We actually specify what we are interested in happening for each of the two trials. All right? And we're going to demonstrate this with a specific example. So my example is, I've got these dice here. You might be able to tell that two of these dice are regular six-sided dice. One is green and one is red. They're numbered from 1 to 6. The other dice I have in my hand are pretty special. These are obviously not six-sided dice. They're 12-sided dice. Their technical name, they're each a dodecahedron. That means they have 12 sides. They're numbered from 1 to 12. And I don't know if you can tell it, but each side is a regular pentagon, 5 sides. Okay? Each face has 5 sides, and there are 12 faces to be technically correct. Okay? And I have 5 of those altogether. 1, 2, 3, 4, 5 dodecahedrons, and only 2 six-sided dice, whose technical name are hexahedrons. But also I could group them in another way. I look at it this way, and then I have 3 green dice and 4 red dice. So there's several ways I can look at this. Well, in any case, I have this sack, and I'm going to place these 7 dice in the sack. So once again, let me move this out of the way. Once again, I would remind you that we have 2 six-sided dice, 5 12-sided dice, or looking at it as green and red, we have 3 green dice and 4 red dice. Okay? Now, let's do an example. Say I would like to know what's the probability that I reach into the bag and pull out a green one and then pull out a red one. Okay, so let's do that. Let me reach in here in the bag and just randomly pick one and pull it out. I get this one right here. Okay? Now here's the big question though. I've got 1 die in my hand. What should I do with this? I've chosen this one. And before I get ready to choose my next one, what should I do with the one in my hand? Should I look at it and put it back in the bag? Or should I look at it and move it off to the side, away from the bag? This is an important decision because the probabilities are going to come out different depending on which one of these we do. If we decide to put it back into the bag, that's technically known as replacement. We replace it back into the bag. If I leave it out, that's technically known as no replacement. Now, when we perform trials with replacement, that is, when I perform trials with replacement, then that means that the trials then become independent of each other. The probabilities of one trial has absolutely no effect on any subsequent trials. If I specify that I'm going to pull these out with no replacement, not put it back in the bag, then the trials become dependent upon each other. That is, the probabilities of a trial is going to depend upon what happened in previous trials. So they are dependent. So replacement gives me independent trials. No replacement gives me dependent trials. Okay? Now, let's do an example of each. Once again, here we go. I'm going to reach into the bag, randomly pull out one, and we're going to do replacement. That means I'm going to look at it and replace it back in the bag. Okay? And let's just try this and see if what we get. Pull one out. It's green. Ah, that matches what my particular event I'm interested in. I wanted a green one. Put it back in. Mix it back up again. We reach in to pull another one out. So I pull out one, and it is, it's green. We didn't make it. We wanted a red one. Okay. Well, in my example, I didn't get exactly what we wanted, but at least we can figure the probability. So let's try. What's the probability that I would have reached in, got a green one, and then replaced it, and then got a red one? Well, remember, with replacement, the trials are independent. So, the probability that I get a green one out of the 7, well, if you recall, let me bring this back if you didn't write it down, there were 3 reds and 4 greens. Okay, so the probability of getting a green one is 3 out of 7. And then the probability of getting a red one, well, the probability of getting a red one is then 4 out of 7. The question is, what do I do with these two fractions? When we were dealing with just one trial, and we didn't care if we got one result or the other, we added the two fractions together. But here, this is a completely different situation. We're talking about 2 different trials, and I'm specifying what I want to happen to the first one, namely a green one, and then I'm specifying what I want to happen for the second one, namely a red one. To get a green one of the first one and then a red one for the second one is a much rarer chance of happening, isn't it? So I want somehow my answer to be probably smaller than either one of these 2 fractions. And the way to get that is to multiply the fractions together. Whenever we're dealing with 2 or more trials with the word "and" in here, which means I want this to happen and then this to happen, we multiply the individual probabilities together. So 3 sevenths times 4 sevenths is 12 sevenths, or 12 49ths. Okay? 12 49ths is my probability. We can expect it to happen 12 out of every 49 times, which is just a little bit smaller than 1 out of 4. Okay, let's do the example where there's no replacement. We're going to reach in here, pull out one, keep it out. So let's do that. Let me reach in here. I've got one in my hand. Okay, I'm going to pull it out, set it over here on the table. Then I'm going to reach in and pull out another one. What's the probability? Let's see what I got. I got a green one first, and then I got another green. Same as last time, huh? Okay, that wasn't what we were looking for, but we can still figure out the probability of this. What's the probability we get a green one first and then a red one with no replacement? Well, once again, the probability of getting a green is 3 out of 7. But now, because of no replacement, there are only 6 in here, so there's only 6 to choose from, not 7. So my denominator is 6. There are 6 possible outcomes. And how many of those outcomes are red? Well, there's still 4 red ones in there. So we have a 4. So my probability now is 3 sevenths times 4 sixths, which is 12 42nds, which does reduce. I'm out of room on the paper. Let me put it up above here. So 12 42nds both reduced by 6. That gives me 2 sevenths. I would expect 2 out of every 7 times that I would get a green one followed by a red one with no replacement.